Well, I should begin with saying that quantum mechanics is one of the greatest discoveries of the previous century. It is a marvelous theory that puts everything in context about the atoms, the molecules, and the entire subatomic world. It is all quantum mechanical. But the strange thing about it is, in spite of the fact that it's so successful in describing the world that we know, it nevertheless doesn't describe anything that looks like reality. So we are used to working with complex equations. So the equations were being discovered and they work extremely well, but then you ask, what do these equations mean? And the consensus that people in the previous century reached was that you simply shouldn't ask. You should just calculate and you'll get the right answers, so why worry? You get the answers that are observed in any experiment, so why worry? And the reason is, I think, that reality is very important if you want to have a theory that sounds more likely to be true than another theory. So if the choice is a theory that describes real things as if they are real as they are, or real things as just mixtures of unreal ghost-like objects, then that theory has a much smaller chance of being correct. So I want to know if the theories we have today actually describe reality or not, and if not, can we cure the disease? Can we make a better theory that does describe things as if they are real? I say as if because subatomic particles are so small and there's so many of them that we cannot really describe them the way they are. That's hopeless. But we can try to describe them the way they could be, and the way their description makes totally sense. Like you talk about stars and planets, you also talk about stars and planets that we never have seen, but we know that they are there. So the same thing about particles. We know that there are too many of them to keep them all apart and to say this one is real, this is imaginary. That's not the way it goes. They're all real. But we want to have a credible model that describes their being real. And this is our difficulty today, that models of quantum mechanics today don't even allow us to do that. And now it becomes more serious. We do something wrong.
So my understanding, as I say, is quite limited, but my understanding is that that is the fundamental problem with quantum mechanics, and so for that reason people are turning to other theories for describing reality. But do you believe that quantum mechanics can be corrected in order to describe reality?
Quantum theory is on the one hand so beautiful it shouldn't be corrected, but our interpretation of quantum mechanics should be corrected, because this interpretation is something which I find not very desirable. It's hard to say why it has to be wrong, but it's just not credible to me. I think with Einstein I like to ask the question, is the moon there if nobody looks? And the answer is, of course the moon is there if nobody looks. What you're talking about. And this is the way I would like people also to talk about elementary particles. Of course these particles are there, and of course this beam of particles that we create is a beam of real physical particles, and some of them move this way, some of them move that way. We don't know exactly where all particles go, every single one of them, but we know how they go on the average. Now quantum mechanics only describes that average and never goes beyond that. But I think we should try to go beyond that and say that this is a realistic scenario of what could be happening and how we could be describing reality.
Well, there's quantum mechanics. You see, now quantum mechanics, it consists of two parts. You see, this is basically I learned from Dirac about the puzzles of quantum mechanics. I think it was partly because I dozed off at the beginning. It wasn't clear, my mind wandered at a certain point. This is his very first lecture.
You dozed off in Dirac's lecture?
No, I didn't doze off. My mind wandered. No, you see, it was right at the beginning, and he was talking about the superposition principle. So you see, if you have a particle, and if one state of the particle is it's here, and another state of the particle is it's here, then you can have states where it's here and here at the same time. Yeah. So you can see particles can be in two places at once. Crazy, but that's how quantum mechanics works. Then he took a piece of chalk, And I think he broke it in two and said, look, the chalk is now, imagined it's here and here at the same time. That was the point my mind wandered, you see, because he gave some explanation. I sort of had the faintest idea what it was. I just remembered something about the word energy coming into it, and I'm worried about that ever since, you see. So why is it that you don't have pieces of chalk in two places at once, or people in two places at once and all that? And this is a big problem in quantum mechanics. So my view was that quantum mechanics can't be quite right.
And Einstein had that view.
Yes, he had a similar view, yes. This is a little bit more specific because it has to do with why is it not right, but that took me longer to think about that. But the view is that it can't be quite right. And the way in which it's not quite right has to be taken advantage of by the brain. So this was the idea that I had, and I wrote this book, The Emperor's New Mind. I thought probably it would disappear without trace, but then Stephen Hawking had written his book on the brief history of time, and he had got, what's his name, Carl Sagan to write a foreword. So I thought I should get somebody decent to write a foreword, then maybe. So I got Martin Gardner. So I had no idea what Martin Gardner's views were. And he said, yes, I agree with you, he said. So he was happy to write a foreword, and then I thought, well, it probably won't disappear without trace.
No, the difference between the two books is that Brief History of Time by Hawking's about that big, and Roger's handy-dandy quick primer for consciousness is about that thick. It's got pictures.
That big. Yes.
But it's interesting.
It is true, a lot of people hated it, yes.
They did. Oh gosh, yeah. Because I was making a series on consciousness at the time, and again, my whole life has been mentioning you and people going like this.
Yeah.
Because the criticism was that all Roger has done is taken a mystery and wrapped it in an enigma and said, there you go. Taken two things we didn't understand and say, because we don't understand these two things, they must be the same thing.
That's not the argument at all. No, they hadn't read the book.
No, and none of them hadn't. That's true.
No, that's true. But the thing is, you see, I had no idea what the answer was. So I wrote the book thinking that by the time I had to learn some neurophysiology and that sort of thing, by the time I'd learnt that bit, I would see where there could be something going on in the brain. See, the argument had to be that it had to be some effect where gravity comes in. And I had no idea at that time. It didn't seem to be that nerve propagation had any chance of being the answer. And the thing is, you see, I was hoping that this book would be read by young people trying to learn about science and so on. Most of the letters I got from people were from old retired people. And those were the people who had time to read the book, I guess. But anyway, not just old retired people. One person who did read the book was Stuart Hameroff.
Yes.
And Stuart Hameroff, his day job is to put people, and maybe at the night too, and to put people to sleep reversibly. In other words, give them general anesthetics when they have operations. And unlike most of his colleagues who were just as capable of putting people to sleep and waking them up afterwards, they didn't seem to worry as much as he did about what they were actually doing.
Yeah.
So this point was, what do the general anesthetics act on? And his view was that they act on these things called microtubules. And so he sent me a letter and he said, well, the thing missing from your argument is you haven't mentioned microtubules. And I thought, microtubules? I get lots of letters from nutty people, you see. And I thought, oh gosh, it's another one. But then I looked it up and I saw that, yeah, they're real. I should have known about them. And these are little tiny tubes. And I thought the chance of preserving quantum coherence at that level was much, much greater than.
But also, in just the last year or two, a lot more people are coming round to this idea, because the problem was always people said, but can you maintain quantum states in the brain? Because the brain is a noisy, messy and warm place, which is generally not good for quantum mechanics. Generally, if we want to do anything with quantum mechanics, we buy a truckload of liquid nitrogen and freeze the entire place down, and then we start. Well, they. And so people didn't like it. But in the last 2 years, a lot of new people are starting, because they've realized actually they can find coherent quantum stuff in the brain where they didn't expect it. So Roger's detractors are all feeling a bit peeved at the moment.
You've written a lot or thought a lot about quantum mechanics, and a lot of people see it as the most accurate, as like giving the most accurate predictions compared to other scientific theories at the moment. But your latest, well, some of your latest work looks at how quantum theory is actually a misnomer. Would you be able to explain this to us?
Right, so there's no doubt, and no one's going to dispute, that there's a mathematical formalism that we know how to derive predictions from, and those predictions can be accurate to 14 decimal places. But what a theory is, what a physical theory is more than just a mathematical formalism with some rules. It should specify a physical ontology, which means tell me what exists in the physical world. Are there particles? Are there fields? Is there space-time? And tell me about those things, and then specify some laws about how they behave, that tell me how they behave through time. And the problem is that there is standard quantum, what's taught as quantum theory isn't a theory in that sense. It's just the formalism. And then what people call interpreting quantum theory, which sounds like a funny thing to do, because you'd say, well, I have a theory, what's an interpretation? What's called interpreting quantum theory is really the development of precise physical theories that make the same predictions, or nearly the same predictions, that you get out of this standard mathematical recipe. And so this, to me, clears up a kind of funny question, because often they say, oh, a physicist would say, well, I've got quantum theory, what do I need an interpretation for? Let the philosophers do the interpreting, whatever that is. And that's because the language is misleading them. No, you don't have a theory. You have a predictive recipe. And what we want, as a physicist, what you should want is a theory, is something that makes clear statements about what the world is.
So does that mean that actually quantum mechanics is a lot stronger in its predictions than the kind of public broad audience thinks? Or does it mean that they're not there yet and they still need to work towards having the status of a theory?
Well, there are different approaches that people have been working on. This is a very minority group who work in foundations of physics. So there's a whole approach that goes back actually to 1925 and Louis de Broglie that's called the pilot wave theory. There's another approach that are called objective collapse theories, and Roger Penrose is working on those, and some other physicists, Giancarlo Gerardi particularly, worked on versions of objective collapse theories. And these are just different theories, and they all make the same predictions insofar as they have been tested so far. So we can't go into a lab and say which of these approaches is right. Even though in principle, sometimes these different approaches make slightly different predictions, you have to think very hard about how you could actually test them.
And what does quantum tell us about physical reality?
Well, that's what's interesting, is that these different approaches would give you different answers. So if I say, well, I think it's the pilot wave approach is correct, I'm going to say, well, it tells me that the quantum mechanical wave function is not a complete physical description, and maybe the world is deterministic, and so on. And if I take an objective collapse theory, I'm going to say that tells me the world is fundamentally indeterministic. And so there's no single answer to that. The one thing we know for sure is that there's a kind of non-locality, and this comes from a theorem of John Bell, which doesn't depend on the interpretation. John Bell proved that just certain results that you get in the lab cannot be reproduced in a theory that is local in a certain well-defined sense. So there has to be some non-locality.
Where do you stand amongst these theories?
I mean, I have a slight, but this is just my preference. My aesthetic sense is that the pilot wave approach seems more natural to me, and the objective collapse approach seems to me more unnatural. But I wouldn't, give a lot of attention to my aesthetic preferences here. They're both very serious. They're trying to write the theory down in completely precise mathematical terms. And everybody should pay attention to all the going things that are actually out there that have a chance of being right.
Look around you attentively. What you see is not what is there. Your sensorial apparatus is being targeted by lots of different signals from the environment. And everything is conspiring to creating a definite, sharp image of this room. The light, the color, position of chairs, number of people, they all have a definite value, all of these properties. And yet, we know from physics that this is not what is really there. All the particles in this room, those that compose your bodies, the photons in the light, and various other things that make sound propagate, phonons, etc., are all quantum mechanical particles. And that means that most of their properties are not sharp, are not definite. Quantum mechanical particles exist in states where if you wanted to measure some of the properties of these particles, most of the times you would get an answer of which you can only predict the probability, but is uncertain, is indefinite. And for this property, I will use the word unsharpness. This is unsharpness of quantum systems. And this is what actually gives the appearance at the macro scale of these definite features that we all can see. So let's take a look. Classically, what we know is that objects have definite properties. So for example, if you want to describe a neutron, you can, for instance, say that a neutron is in a particular position, 0, or it's in a different position, 1. These two positions are distinguishable. You can also assign an energy to the neutron and lots of other properties, spin, etc., and they're all definite. Quantum mechanically, picture is completely different. There is a state where the neutron is in position 0. There's a state where the neutron is in position 1. But also, there is this particular state here, which I represent pictorially like that, where we can only predict the probability for the neutron to be in position 0 or 1, but the position is unsharp. And these states are called superpositions. And notice that this unsharpness has nothing to do, or has very little to do, with stochastic uncertainty, like when you throw a dice. This is a different type of unsharpness, is richer. And this is why it's the key property that powers all of quantum mechanics features, including those that are used for quantum computers, for quantum cryptography, and for properties like entanglement that are extremely exotic and different from what we perceive. Now, this unsharpness is mind-boggling. It's a very beautiful feature of these quantum systems, but is also a source of very interesting problems. And one of the most interesting problems comes up when we try to ascribe this unsharpness to objects which are demanded by other physical theories to be sharp all the time. And this is the case of gravity. Now, general relativity is this theory that Einstein came up with to describe masses and the way they interact through gravitational forces. And relativity, theory of gravities in general, have no unsharpness. They want their objects to be all the time sharp in their position, their energy, all of their features. So when you want to describe, for instance, the interaction between two masses, like this, you can only describe this if you can assume that these masses are fixed and have definite positions, and then they interact with respect to one another through gravitational interactions. General relativity can't take the unsharpness of quantum theory. So, for example, what happens if instead of two sharp masses in sharp positions, you have masses that are in quantum superpositions of different locations? So, quantum theory requires every object to be capable of being in these superpositions. So we have to consider these states if we believe in quantum theory. But at the same time, if we believe that these are masses and that they can gravitate, they should also obey general relativity. But general relativity doesn't allow these type of states. It can't deal with this. So there's a big question mark there. And physicists are scratching their heads about this. What is going on? How do we describe this?
Well, for a long time we've heard these stories about how quantum mechanics is weird, and how there is this subatomic world or this atomic world that obeys different rules to the ones we're used to, and we have stories that we tell about that, about how particles can be in two places at once and how they can mysteriously communicate to each other over long distances and so on. And what I'm saying in my new book is that we need to change those stories. We need to change the record, really. And part of the reason for that is that the field hasn't stood still. The questions at the heart of it are the same ones that people like Niels Bohr and Albert Einstein were grappling with when they invented this quantum mechanics. But we know more now. And particularly we know more because some of the experiments that were just thought experiments in their day, we can now actually do with today's technologies and have done. And so we don't necessarily have all the answers about what quantum mechanics means, but we have much better questions. We've refined the questions. And I think this has shown us that these old ideas about particles being in two places at once or taking two paths at once or whatever, they're just our classical attempts, so using analogies from our everyday world to try to develop some language to explain what's going on. So I understand why we have them, but actually they're missing the point. The whole point about quantum mechanics is that it's not classical, that particles don't in any obvious way just take paths through space or just are here or there. Quantum mechanics is counterintuitive in a very profound way, and we need new stories to grapple with that. And one of the ways I think we can start to think about it more productively is in terms of what is knowable and what is not, in terms of information, but in particular in terms of the information that we have access to or that we don't have access to. And one of the productive ways that physicists are now thinking about this is in terms of perhaps there being some imbalance between the number of questions we can ask about a quantum mechanical system, a particle or whatever, and the answers it can give us. That it can't actually, at that quantum level, the world can't give us unambiguous answers to every question we can ask. And when it doesn't, what we seem to get when we sort of run out of answers is just randomness. And the result of that is that things look very strange from our everyday point of view. But we need to sort of shift the thinking away from how it usually works in science, where we think, I'm going to interrogate this system, I'm going to ask a question, and I'll get a result. In quantum mechanics, you don't always do that. So asking, what is this particle like and what is this particle like, you think you should get two answers out of that. But in quantum mechanics, it seems like there are occasions, many occasions in fact, where those two particles aren't actually two particles. They're kind of the same thing, even though they're separated in space. They're you have to think of them as a single entity. And so there's not enough information in that single entity to give you answers to those what seem like independent questions, because they're not independent. They're dependent on each other. I think this, it seems to be what's at the heart of quantum mechanics. So it's really about what questions we can ask and how much information we can expect to get in response to those questions.
So how can we invent a language that suits quantum mechanics better than our current use of language? Have we already made some small steps in that direction?
Well, at the moment, and science has to do this and does it all the time, particularly at the frontiers of physics. At the moment, we invent terms that patch over our ignorance. Dark matter is a term like that, dark energy is a term, and so is, we talk about in quantum mechanics, quantum non-locality, which basically refers to this idea that, to put it one way, the properties of a quantum object aren't all located on that object. Some of them might be kind of related to the properties of some other object. It's as though those properties themselves are smeared out, as though, you know, the goldness of my ring is somehow not just in my ring, it's also in this other object over here. And we say that's quantum non-locality. So there's a word to talk about it, and it's useful to have that word because it stops us then saying, well, but it has to be in this ring. You know, we say, no, it's non-local, so it's not, you know, it's somehow space is messed with here. And sometimes time is messed with in similar ways in quantum mechanics, but it's just a word. And, you know, we don't have an intuition for it. And, you know, we talk about that also in terms of a property called entanglement. These two objects are entangled together. It's a nice descriptive word, but what does it really mean? So at the moment, we're at that stage. We can invent words that stop us from telling these old stories, or they should stop us from doing that, but they don't really give us an intuition of what's going on. And I'm not at all sure that we'll get past that because of this fact that, of course, our language is the language that you have when you're 6 feet tall and you're living in a classical world. If we were electrons and protons, we would have a language to describe these things, but we're not.
For more debates, talks and interviews, subscribe today to the Institute of Art and Ideas at IAI TV.